Welcome to the course on FPGA based signal processing systems. As we are doing this arithmetic basics, we had seen the number systems and a few basic number systems and the full adder operation. So how this full adder operation is reduced with the lookup table and the mux structure, where the carry generation is made high speed, the fast carry generation. So in the addition process, the adders play an important role, in which sum can be obtained as soon as A and B bits are given, whereas the carry needs to be, which adder type we use, that carry needs to be propagated for n bit adder, or carry, how to deal with the carry and how to generate the carry faster. That makes the addition process faster. So in that line, we'll be looking at some of the techniques which is used in the addition process, especially for high speed operation. One is that we can have this prefix computation. Let's see this algorithm, how the prefix computation is done, especially for the basic thing. Suppose you have this n bit number. The numbers are the data which is coming in. You have a set of data, or 5 data, 8 data, or this is for instance, you are getting 1 by 1, 1, 2, 3, 4, 5, 6. Okay, so then what is the we want to compute the sum of these numbers. Okay, so then how to do it with the prefix sum. So prefix sum is the operation in which the first data which has just come is just taken 1, and that is assuming the previous ones are 0, previous data is 0 and stable. And then this one, the next data is added with this sum, so get the second sum. So 1 plus 2, 3, and then with this 3 and the next sum is added to get 6. So for the 6, the 4 is added to get 10 and 15, and the 15 plus the 6, we have this 21. So this is prefix sum. If we add all of them here, 3 plus 3, 6 plus 4, 10, and then 15 plus 6, 21. So instead of storing all of this and adding, our data received by one can also be added in this case, and the total sum which is getting at the nth data is the 21. That is called the prefix sum. So if we take the equation of it, the first sum y0 is simply x0, what is the input, and the second sum y1 is x0 plus x1, the second data, and y2 is x0 plus x1, that is y1, which is obtained over here, plus this x2, and similarly y3, which is having the y2 plus x3. So this is the, and yn at the end stage, we have the n minus 1 inputs added, and then the nth addition can be done with this if we have the data which is streaming. So this prefix computation and the recursive doubling technique, or the recursive doubling technique can be used for prefix sum computation. Suppose prefix sum here, if you take this, takes n stages, so it depends on this 3, 6, there are 6 datas here, so it takes the 6 steps to compute the prefix sum. So whereas, can we reduce this number of steps in the addition process? Yes. So that is the one procedure which can be used, is this recursive doubling technique, to compute this prefix sums. So to compute the prefix sum of 8 numbers, like we take this numbers which are coming in, that is, this is the first data, second data, and then data is, we can say data 1, 2, 3, 4, 5, 6, 7, 8. There are 8 datas over here, and then 8 numbers we want to compute the prefix sum in this case. So if you just add it, all of them, then you would get the sum, and or the prefix sum, taking it one step, adding this to, and then add the other one with the sum, and add this to the previous sum, add the next one to the sum, and so on, we can get at the end. So considering this input, if there is any previous stage input, or the carry which is stable, and taking it that as 0, so in this case the data is in this entering in this fashion. So let's say in the next step, in the recursive doubling technique, which takes log n steps. Okay, so the next step would be how do we go about this recursive doubling? So in the process of reducing the number of steps in the prefix computation, so next we will be taking this 8 and 7. Okay, so 8 and 7, submit and keep it at 8th place, and 7 and 6 at this place, and then 6 5 and the 6th place, 5 and 4 at 5th place, and 4 and 3 at the 4th place, 3 and 2 at the 3rd place, 2 and 1 at the 2th place, 1 and 0 at 1 place, and 0 can be copied. So this is how it is given, that the addition process is between consecutive two consecutive numbers, 8 7 7 6 6 5 and so on. So if we take this, this is the step 1, and step 1 is just take the data and add the next one in data. So the step 2, which is the resultant of the previous one, this is giving that 8 and 7 32 and minus 15, which is giving the sum as 17. Similarly, the next sum, 7 and 6 resulted in minus 9, and then this is the one with 6 and 5, 8 7 7 6, and then 6 5, and then 5 4 result in 5 4 3. If we add it, that is giving 15, 3 2 3, and then 2 1 minus 4 1 and 0 1. So this is the step 2 which we obtained from the step 1 by adding the consecutive two numbers, and then that is we can say it as 2 power 0, that is the 0th step. Then in this case, what we will do next is that take the 8 and 6. Okay, so we skip 1. Okay, we skip 1, 2 power 1, in that one is skipped. Okay, and then so we add 7 and 14, 7 and 4, keep it at 17. Okay, and then we add 7 and 5, keep it at 7. Okay, 8 and 6, 7 and 5, and then 6 and 4, keep it at 6th place, and 5 and 3, keep it at 5th place, and then 4 and 2, keep it at 4th place, and then 3 and 2 at 3, and then 4 and 0, this minus 4 and 0, which is place 2 and 0, and if you get the resultant here, 17 plus 4, that is going to be 21, and this number is minus 9 and plus 5, which is going to be minus 4. Okay, and then this is 19 and 8, and here it is 11, so this is 4 and minus 4 here, 1, and so on. So this we will get it. We'll get here the outputs. Just want to see 21. You can see 21 minus 4, 19, 8, 11, 4, minus 4, and 1 and 0. This is obtained by skipping in between one of the data. Okay, so this is the outcome of the step 2, and the step 3 would contain, obviously here what we have is the next one, 8, and then skip this 3 of them. Okay, and then 7 this 8th place and 15th place, add it. Okay, and the 7 and 1 2 3, skip it, and 3. Okay, so like this we added 6 1 2 3, skip it, and then 2 6 and 2, and then 5 and 1 2 3, skip it, 5 and 1. So add them, and the remaining in the 4, you don't have this 4 and 0, and 3 also should be added to 0. So just copy them with it over here after that. So if you have this is the next step, 0 1 2 2 power 0 1 2. This is skipping the 3 in between, and the 4th one is added with the first one. So in that process we get, this is 21 and minus 4, 19, and so here we get 21 and 11, and then minus 4 and 4, and then 6 2, so 8 and 1, and 11 and 0. So we get this resultant would be the 4th step, that is 32. This next one is 0, 15, 9, 11, and so this is the addition of 8 and then 4 and then 7 and this third, this positions, and 6 and the 2 is the next position, and 5 and the 1 is the next position. So it goes on. This is the outcome of step 3. And now next step, which is next step here, this is the 8, and then skip 1 2 3 4 5 6, and then here we have this 1, and then rest of them would be same. So it is going to be 2 power 3, and so it has had that 8 minus 1, so 8, and the 1 will be in between, the 7 of them will be skipped. So the final step would be having the 8 and this thing. So you have this next step, this is having the 32 itself. So here the process is complete and you get the outcome as 32. So the sum of these numbers is 32. So what we get from this is the log n steps. You have this within the 4 steps, you can get the output. Okay, so which is going to is here. The initial step is suppose that 0. So if you have if you have n numbers, that is prefix of n numbers, it is the summation can be obtained with log n steps. So the steps what we have used is in the first one consecutive number, and then skip one data in between, and skip 3 in between, and then 7 data are skipped, and first one and the 8th one added, and so on. So here is the one which we have. So 7 skipped and then 0. So this is the 32. So the sum is 32. So from this technique, we have this prefix sum is computed using the recursive doubling technique, where you have the n numbers, it is taking log n steps. So 3 steps, at least the first step, then the 4th step you get the output. So if we use this prefix sum computation for prefix carry, can we use that, and shall we use this recursive doubling technique in that? So if we use prefix sum alone, it takes n steps. Okay, so here the number of steps in the recursive doubling technique gets reduced, so the high speed carry operation can be done, so the carry can be obtained in a few steps. So it is applicable to all semi group operators. If you learn this min, max, add, and those are associative in digital electronics, it must have gone through. So this is the high speed addition. Let's see that how this can be. So for example, if you have this n bit carry ripple addition, so 4 bit we had done, if you recall that the example, that is 2 bits, 2 numbers of n bits, so shown over here. So you need 0 to n minus 1 full adders. This will not take any carry, so this can be a half adder. If you use it for subtraction, yes, this needs to be a full adder, because we need the carry to, this one should be minus, we'll keep that 1 as a carry in. So this 1 or 0, so depends on the adder or addition or subtraction. So the input here, the third input. So the n bit carry ripple addition, so carry is propagating from one to another, you can see, and at least it should ripple through n minus 1. So 1, 2, suppose it is 3. So if it is n equal to 4, then at least 3 ripple throughs needs to be allowed, and then it takes time. So number of gate delays involved in each full adder to generate the carry. For one carry, after that this can find the sum, but the carry needs to be added and then getting it through. So this how to make this as a high speed addition in this process. It requires n steps, right? And that so instead of that, can we have this in few steps? So the lookup table, or we used that in the previous lecture, the mux structure. So we have reduced this to the mux structure, in which the 1 bit full adder, if you recall that this is 0 0 and the carry, the another input is 0, the next carry Ci plus 1. Here sum is neglected for the discussion, that sum can be calculated at the previous case we can use it, the truth table which is given. Now the for carry operation, so if a and bi, in this case these two are equal, and here also a and bi are equal, then this Ci plus 1 is either a or bi. So that's what we did the previous lecture, that is bi, it was equal to bi or ai, anything. So this is a or bi, this two cases, this I plus 1 will be, so here ai or bi, both are same. And if these two are not, so if it is not bi, then the Ci plus 1 is simply Ci only. So this is the case which led to the case of mux structure instead of those gates in the full adder. So from this logic which can we have this carry look ahead? Can we compute that as a carry look ahead addition instead of having the ripple through here? So in this case, carry look ahead, if we see an A and B, the Ci plus 1 is also 0, either A or B. So this is if both are equal. In this case it is 0. So if both are equal, this condition and this condition, this is Ci plus 1 is equal to either A or B. Whereas if both are different, that is it's not equal, then this is going to be the previous the carry what is coming in, Ci and Ci. So the in case of I plus 1 stage, so if we are computing this in bit 1, how do we consider them here? So suppose this is, if the carry of this is to be considered this as kill, and if we have Ci and Ci, just propagate that PP, and then 1 is generated. So we must have learned this, propagate and generate. So propagate and generate, we call this P and G, and additionally if the carry is not involved, then they call this as kill or K. So in this way we can, using that logic, we can generate this carry, propagate and generate. So using the table and the prefix computation, we can have the carry look ahead here. So the CLA operation, which can be simplified, the tabulated here, is if this xi, the carry is a kill, and this is an associative property, and I plus 1 was k also, then what should be the resultant in the next stage was, will show you with the example so that do not confuse with I and I plus 1. So k and k, if it is the first and second bits which is deciding the next carry, so in that case this is k. If it is kill, and again this is not going to allow the propagate, and if generate, yes, in all the cases it would generate. This propagate, and both the sides it would be propagate only, even though it is propagating, and next stage would can kill it, and generate also can kill this, no carry to proceed further. In this case, generate and propagate is not propagate, it is generate. So see the difference between this. This table would help the CLA operation, which is associative. I plus 1 carry status is influenced by ith one, which is associative. So we can consider this, suppose the yi, which stage you want to compute, like a prefix sum, x0, x1, x2 are up to ith stage is associative. So the asterisk implies that this is the prefix carry computation. So initial stage, which take this as k. So from this, how do we do the carry calculation? So in the prefix computation, if you remember, y of 0 is x of 0, which is considered to be k, and y of n is the carry computation x of 0 and x of 1, and x of 2 is again taking y1 and x2 carry operation, and then it continues up to n stage if we use only the prefix computation. So instead of that, if we use the parallel prefix circuit, like that take this xn x1 to xn for all an n bit CLA carry look ahead, so that x0 can assume that as k if there is no carry in, and if there is a carry available, make this as generate. Okay, so with this, using the recursive doubling technique can be reduce the number of steps in carry calculation. Okay, so for example, if we take add two binary numbers, these numbers can be of any two numbers with, this is having 7 bits, you can have this 8 bits as well. So if we add them, so just to show the problem in sum and carry calculation, if we have this parallel prefix, carry is generated separately, sum is generated separately, and then adding the two, so that doesn't work. So let's see then an example. So this is 0 1, adding them it is 1 1, and 0, there is a carry over here, so we have 0, and then there is 1 carry, 1 with this carry, the sum is 1, and it is having, this is the addition of these two numbers expected. The final one should have 1. So can we do it, generate the sum in parallel? Can we do it this way? So just adding these sums here, that is here 0 1 1 0 0, if there is a carry, ignore that carry, and 1, and there is a carry, ignore it, 0 and there is a carry, ignore it. So this is the sum. Okay, so after this, if we have this, in this case you ignore the carries here and generate the carries in parallel. So now, so just having this sum over in sum, and then the carry alone, this stage doesn't generate any carry, this stage also doesn't generate any carry, and here yes, there it is generating a carry, and here no, and here there is a carry, and this stage there is a carry. So this is the carry now generated separately in the parallel operation. So carry sum separately and carry separately. So can we add this sum and carry for the, and then if there is any the sum which is for this in two numbers, the sum obtained is the one is this, and the carry is this. So if you just shift the one, so that we add it 1 1 and then 1 1 0, if there is a carry, then that this would generate a carry actually in this place. We ignore that carry, so this is becoming 0 and 1 and 0. So rest of the bits are okay. This is not correct in this case, so we'll not be able to generate that in parallel like this fashion, separately add them. Okay, so there is a mechanism which needs to be taken care in this, to add the sums separately and then generate carry separately and add them. So how do we rectify this? So we can use this prefix idea to get this carries. So here generate the sum in parallel, so that, and keep aside. So generate kp or g also in parallel. Okay, so and then do the parallel prefix carry computation. So how we can do it in this case? So this would solve the prefix computation of generating the carry, would solve the problem here. So let's see that. Suppose this same numbers we had taken 0 1 1 0 1 1 1 0 1 1 0 0 1 1. So how do first stage is how we are going to use this recursive doubling technique in the prefix computation of carry. Okay, so the case here is the A and B are different. Okay, so these two are different and this is same, and here different, and then this is same, and these two are same, and this is same. Okay, so you can see this, and you have the carry will be generated here. The first stage we take this K, and 0 1, yeah, there will be a propagate stage. If you look at the previous case in carry look ahead, we have got this stage leads to propagate if these two are propagate, and 1 1 would lead to the generate case, and then 0 1 again the propagate, this is generate, and 0 0 if you have there is no kill, and 1 1 would lead to generate. So this is the first stage we use it, and then the carry in, if you have this, if the carry in is available, make this as generate 1, carry is available, otherwise. So using this one, now we will use the recursive doubling technique, that and then fill the next rows, so taking the subsequent numbers like in the first stage of the recursive doubling technique, use this 1 1 and 1, this 2 3 and then 4. So if we take the first stage here, the K, all the first stage is propagate, generate, and then propagate, generate K and generate. So after making the first stage, we'll to the step 1, that is K, this K and P. So consider this as I and this is I plus 1. Okay, so this is I, K and P, which results in K. Okay, here similarly P and P, this is P and P, which is propagate over here. So generate, this is I, the stage which is P, and I plus 1 is G, the next resultant would be G. So P and G, the generate over here. Similarly G and P also would be generate and propagate is also generate, not the propagate. P and G is also generate and kill and generate will be generate. So this one, last one. So the second stage is obtained. So the stage 1, getting it from the whether from 2 bits of the inputs A B, how this whether the carry will be generated at the first stage or it will be propagated or there is no carry. So, and after that, this uses the recursive doubling technique. And the next stage is copy. Then we have this. So if we have the one skip the next step, that is, here is P and then this is from K. So in between this step is, you can copy over here this K and P, which results in K. So K, P, which is K here, and for the next is generate, you can here K and generate, this is generate K and generate. So similarly generate and P, the I was P and then generate was I plus 1, so which also gives the generate. So PG, which is this case. So here generate and generate would give this skipping 1, and then K, this skipping this G and K, which is K, generate and generate this skip this K and G. So this is step 0, 1, 2, and then the final step, because we have the 7 or 8, three steps we can get it. So the final step, we have the, instead of skipping 1, skip the here once here. So this is K again here, copying it, and then you can have this 3 skipped. Okay, 1, 2, 3, K and G. So this is the first point you get from this K and generate. It is going to be generate, and the generate and K, which is again generate K. This one is again, previous stage was K, so kill and then generate, and generate gives G. So this step, you can see there is all propagates are eliminated here. Okay, so kill will correspond to 0 and generate will correspond to 1. Okay, so assign the bits of this. In this case, this is 0 0 1 1 1 0 1. So that is the carry which is generated for this particular two numbers. Okay, so this is over here 0 0 1 1 1 0 1. Okay, so after assign this bits, the propagate will be eliminated totally in this process. So K, G you will get in terms of the K and G. So the addition process, how do we get it? So two numbers, take the sum separately, and the carry what we get is 1 0 1 1 0 0. You can see over here 1 0 1 1 0 0. So shift this position 1 and add it now. Okay, if there is any carry, ignore that carry. So this position is set right now 1 1 0, this is 0, and here this is simply 1, the carry, ignore the carry here, 1 1 again here, this is only giving 1 0 1. So this is the sum which is expected in the addition process. Okay, so we get this right. So what we had used in this lecture is the addition process, in which the sum can be generated and the carry can be generated in parallel, that is parallel prefix circuit. Using the prefix sum computation and the recursive doubling technique, we reduce the number of stages involved in the carry computation. So the carry can be generated very fast, for the depends on the number of bits. So I have shown is a 7-bit, it can be an 8, can be 16-bit also. So the numbers, if it is huge, this would reduce number of steps in carry calculation. So we'll see this addition process, how it is affecting the time delays and in the addition. So how we can because this is also involved in the timing analysis of the circuit. When you dump the code in this FPGA, this would also find, you need to find the critical paths and so on for the design circuit. So it is helpful to reduce the number of steps using this in the addition process, so that the addition can be faster. Thank you.